These are the types of small scale fading, and based on this multi-path time delay spread, we have two categories, that is flat fading and frequency selective fading. In flat fading, the bandwidth of the signal is less than bandwidth of the channel, and in frequency selective fading, the bandwidth of the signal is greater than bandwidth of the channel. And here the delay spread in the case of flat fading is less than symbol period, and in the case of frequency selective fading, delay spread is greater than symbol period. So now we'll learn about the fading effect due to multi-path time delay spread. Based on that, we have two categories, that is flat fading and frequency selective fading. So this fading effect due to this multi-path time delay spread, the time dispersion due to the multi-path causes the transmitted signal to undergo either flat or frequency selective fading. So based on the time dispersion of this multi-path, we have either flat or frequency selective fading. So going on to the flat fading. In flat fading, if the mobile radio channel has a constant gain and linear phase response over a bandwidth which is greater than bandwidth of the transmitted signal, then the received signal will undergo flat fading. So if the bandwidth of the transmitted signal, that is if the channel has a bandwidth which is greater than bandwidth of the transmitted signal, so channel bandwidth is greater than signal bandwidth, then we have flat fading. That is if the mobile radio channel has a constant gain and linear phase response over a bandwidth, that is a channel bandwidth which is greater than bandwidth of the transmitted signal, that is a signal bandwidth, then the received signal will undergo flat fading. So if the mobile radio channel has a constant gain, that is the channel bandwidth has a constant gain and linear phase response over a bandwidth and which is greater than the bandwidth of the transmitted signal, then the received signal will undergo flat fading. Here in flat fading, the spectral character of the transmitted signal are preserved at the receiver. Here we can see that this is the figure which shows the flat fading channel characteristics. Here this S of F is the transmitted signal and R of F is the received signal. Here we can see that S of F, R of F is similar to or it is identical to S of F. Here all the channel characters or the signal character are preserved at the receiver. That is in flat fading, spectral character transmitted signal, that is S of F, here all the spectral character of characteristics of the transmitted signal are preserved at the receiver, that is R of F. However, the strength of the received signal changes with time due to the fluctuation in the gain of the channel. But the strength of the received signal, that is received signal R of F, the strength may differ due to the fluctuation in the gain of the channel. So in flat fading, the channels are also known as amplitude varying channel or narrow band channel, since the bandwidth of the applied signal is narrow as compared to the channel flat fading bandwidth. So here this flat fading channel are also known as amplitude varying channel or narrow band channel, since the bandwidth of the signal which we are applying is narrow compared to the channel bandwidth of the channel, and so it is known as flat fading bandwidth. And here a signal undergo a flat fading if and only if the bandwidth of the channel signal, that is BS, is less than bandwidth of the channel BC, and TS, which is a symbol period, which is greater than RMS delay period, that is tau C. So BS, if it is less than BC, then we can say that flat fading can occur, and if the symbol period TS is greater than the RMS delay spread, we say that flat fading can occur. Here we can see in the figure that here this is the S of F. Here H of F is our channel. So S of F bandwidth is less than H of F. So only a little fading occur, or the fading is reduced in the case of flat fading. And here we can see that S of F is similar to R of F, which is a received signal. And here all the frequency component are fade equally. In this flat fading, all the frequency component fade equally, and this is all about flat fading. Here we can see that signal bandwidth is less than channel bandwidth. So ഇവിടെ എല്ലാ component, all the frequency component എല്ലാ ഫ്രീക്വൻസി കോമ്പൗണ്ടിലും ഒരേ ഈക്വൽ ഫേഡിംഗ് ആണ് ഈ ഫ്ലാറ്റ് ഫേഡിംഗിൽ occur ചെയ്യുക. This is about flat fading. That is, if the mobile radio channel has a constant gain and linear phase response over a bandwidth which is greater than bandwidth of the transmitted signal, then the received signal will undergo flat fading. In flat fading, the spectral carrier of the transmitted signal are preserved at the receiver. As we can see, R of f is similar to S of f. Only the change is in the strength of the received signal, and the strength of the received signal varies due to the time fluctuation in the gain of the channel. And the flat fading channel are also known as amplitude varying channel or narrow band channel, since the bandwidth of the applied signal is narrow as compared to channel fading bandwidth, and the signal undergo flat fading if BS is very much less than BC, that is bandwidth of the signal is less than channel bandwidth, and if TS, that is a simple period, greater than the RMS delay spread. Now we will move on to the next category, that is frequency selective fading. Here, if the channel has a constant gain and a linear phase response over a bandwidth that is smaller than the bandwidth of the transmitted signal, then the channel undergo frequency selective fading. Here it means that frequency selective fading occurs when the channel bandwidth is less than transmitted signal bandwidth, or if we can say that if the transmitted signal bandwidth is greater than channel bandwidth, then the frequency selective fading occurs. Here, if the channel has a constant gain and linear phase response over a bandwidth, and this bandwidth is smaller than the transmitted bandwidth, then the channel undergo frequency selective fading. And here this term, it is known as frequency selective because here not all the frequency component undergo fading, but only a particular frequency component or components undergo fading. Not all the frequency component undergo fading. So this is known as frequency selective. As the name frequency selective, it indicates that not all the frequency component undergo fading. Only a selected frequency component or selective frequency component undergo fading. So this frequency selective fading is due to the time dispersion of the transmitted symbol within the channel. This, as we have said in flat fading, it is due to the time dispersion of the transmitted symbol within the channel. Thus the channel induces ISI, that is inter symbol interference, in this frequency selective fading. There will be inter symbol interference, and this when this fading occurs, when the frequency selective fading occurs, the received signal induces a multiple version of transmitted waveform that are attenuated and delayed in time, and hence the received signal is distorted. This figure shows the frequency selective fading. Here we can see that the bandwidth of the signal is greater than the channel bandwidth. H of f is the channel impulse function. So we can see that S of f is greater than H of f, or have a greater bandwidth, or the transmitted signal have a bandwidth which is greater than channel bandwidth. Hence, only a small portion, and we can see that received signal R of f is different from S of f, what we have transmitted. And we can see that only the fading occur in the case of both the rising edge and falling edge. We can see that by comparing these two, this S of f have a larger bandwidth compared to H of f, and the fading occur in the rising and falling edge. Here this H of f, this region is flat. So this flat region or the flat frequency component does not undergo any fading. Only the rising frequency edge and the falling frequency edge undergo fading. So the frequency selective fading is due to the time dispersion of the transmitted signal within the channel. Thus the channel induces ISI. Here this frequency selective fading induces inter-symbol interference, and when the fading occur, or when the frequency selective fading occur, the received signal induces a multiple version of transmitted waveform that are attenuated and delayed in time, and hence we say that the received signal is distorted. Usually in the received signal, due to the multipath propagation, we are considering here the multipath propagation which have multipath time. So each signal which is transmitted undergo multipath component, like reflected component, there will be diffracted component, and there will be scattered component. All these components arrive at the receiver at different time. LOS component, if LOS component arrive at 10 seconds, means after 5 seconds the reflected component arrive at the receiver. After 5 seconds the scattered component arrive at the receiver. Again, after 5 seconds, the diffracted component arrive at the receiver. So there is a multi-part time. There's a time delay between all signal arriving at the receiver. So due to this, when this fading occurs, the received signal include multiple version of transmitted waveform. That is, multiple version here indicate that is from reflected, refracted, and scattered component, and are attenuated and delayed in time, because the starting time or arriving time or receiving time of all this multiple component is different, and hence they are attenuated and delayed in time, and hence the received signal is distorted. Here we can see that a signal R of F, which is the received signal in frequency domain, which is different from S of F, and here we can see that the channel bandwidth of the transmitted signal is greater than the transmitted signal bandwidth is greater than channel bandwidth, and hence we can say that frequency selective fading occurs. This is about the small scale fading due to multi-part time delay spread. So due to multi-part time delay spread, we have studied two types, that is flat fading and frequency selective fading. Now we will move on to the next type, that is due to the Doppler shift. And here one more thing, for a frequency selective fading, the bandwidth of the transmitted signal is greater than the coherent bandwidth of the channel, that is BC, and the frequency selective fading channel are also called as wideband channel. Flat fading channel or flat fading channels are known as narrow band, but frequency selective fading channels are known as wideband channels, since the bandwidth of the signal, that is the transmitted signal bandwidth, is wider than transmitted or wider than the bandwidth of the channel. That is the impulse response of the channel. So S of t, if it is greater than channel bandwidth, that is the bandwidth of the signal, S of t, if it is greater than the channel bandwidth, then we can say that the channel is known to be wideband channel. And if S of t or the bandwidth of the signal S of t, if it is less than channel bandwidth, then we can say that the channel is narrow band channel. And the signal undergoes this frequency selective fading if this transmitted signal bandwidth is greater than the coherent bandwidth of the channel, and if the symbol period Ts, it is less than RMS delay spread. As the time varies, the gain and the phase of the channel varies at the received signal is distorted. And next is due to the fading due to the Doppler spread, and depending upon this Doppler spread, or depending upon how rapidly the transmitted signal changes as compared to the rate of change of the channel may be classified into two types, that is fast fading and slow fading. And in fast fading, we have a higher Doppler spread, and in slow fading, we have a lower Doppler spread. And going on to the fast fading channel, the channel impulse response changes rapidly with the symbol duration. Here, the channel impulse response, in the fast fading, coherence time means it is less than symbol period. So the channel impulse response changes rapidly with the symbol duration. And the coherence time of the channel, here it is smaller than the symbol period of the transmitted signal, and this causes a frequency dispersion due to Doppler spreading, which leads to a signal distortion, and the signal undergo this fast fading if this Ts, which is the symbol duration, is greater than coherent channel duration, that is EC, and if it is Bs, that is transmitted signal bandwidth, it is greater than Doppler shift. So next is slow fading. In slow fading channel, the channel impulse response changes at a rate which is lower than transmitted signal bandwidth, that is S of t, and a signal undergoes the slow fading if this Ts, which is very much less than Tc, and if it is Bh, which is very much greater than this Bd. So this is about the slow fading and fast fading. Here the figure shows the two categories, that is in case of symbol period of transmitting symbol, basically we have Ts. So in comparing to this Ts, we have two types, that is flat fading and frequency selective fading. So we can consider this Ts here we have a tau-c delay spread. So if Ts is greater than this tau-c, we can see that it is a flat fading of if the signal in the bandwidth is less than channel bandwidth, we have flat fading, and if the signal bandwidth is greater than channel bandwidth, we have frequency selective fading. So based on this two category, we have we have flat fading and frequency selective fading. In flat fading and frequency selective fading, we have studied that in flat fading, we have studied that flat fading occurs when Ts is greater than this tau-c. So we can say that when this Ts is greater than this tau-c, that is upper portion corresponding to this tau-c. When Ts is greater than tau-c, this portion belongs to flat fading, and when this Ts is less than this tau-c, then this region belongs to slow fading. So based on this Ts and tau-c, that is the RMS delay spread, we have flat fading and frequency selective fading. Now we will discuss about the fast fading and slow fading, that is based on the Doppler shift or the Doppler spread. So based on this Doppler spread, we have two categories, that is Ts and Tc and Bs and Bd. If Ts is less, now we can consider a new axis Ts which have a value Tc. When this Ts is greater than this Tc, we have fast fading. So this region we have fast fading. When this Ts is less than this Tc, we have slow fading. So this region is slow fading. So the upper region corresponds to flat fading and lower region corresponds to this frequency fading, and this right hand side corresponds to fast fading and this left hand side corresponds to slow fading. So this fast fading and frequency flat fading and this frequency selective fading is based on this Ts and tau-c value, and this fast fading and slow fading is based on this value Ts and Tc. Now transmission bandwidth signal transmitted baseband signal bandwidth. So now we will discuss about the corresponding to the bandwidth of the signal. So here a Bs corresponds to bandwidth of the transmitted signal and Bc corresponds to the bandwidth of the channel. So if Bs is greater than Bc, we have frequency selective fading, and if the Bs is less than Bc, that is if the transmitted signal bandwidth is less than channel bandwidth, we have flat fading. So this graph corresponds to based on this Bs and Bd and Bs and this Bd, that is baseband Doppler shift in the baseband, and this corresponds to symbol period of transmitting signal, and based on this RMS value of this delay spread. So, and if Bs is greater than this Bd, we have frequency slow fading, and this region corresponds to slow fading, and if this Bs is less than this Bd, we have fast fading. So this is based on, that is both this figure shows a matrix illustrating type of fading experienced by signal as a function of symbol period, that is first shows based on the symbol period and second shows based on the signal bandwidth, that is Bs, Bc and this Bs and this Bd. So this is about the fading types based on this multi-path time delay and Doppler spread. So we have, if Ts is greater than this tau-c, then we have flat fading, and if this Ts is less than tau-c, we have frequency selective fading, and if this Bs is greater than this Bc, we have frequency selective fading, and if this Bs is less than this Bc, we have flat fading. And now going on to the, based on this Doppler spread, if this Ts is greater than Tc, we have fast fading, and if the Ts is less than this Tc, we have slow fading here. And corresponding to the bandwidth, if Bs is greater than this Bd, we have slow fading here, and if the bandwidth is less than this Bd, then we have fast fading here. So this is about the fading effect and types of small scale fading. Now we will move on to the diversity technique. So this diversity, it means it's a powerful technique that provides wireless link improvement at relatively low cost. So diversity means one or two paths. So if one path fail, we can achieve signal from the other path. So based on this diversity is a improvement at relatively low cost. If one path undergo a deep fade can be frequency selective fade hour, fast fade hour, slow fade hour. So if one of the path undergo a deep fade, another independent path may have stronger signal. So we have multi-path propagation. So if one of the path undergo a deep fade, another independent path may have a stronger signal. So by selecting the best signal at all the time, the fading effect can be reduced. So we have to select the signal from the path which does not have a deep fade. That in the case of flat fading and frequency selective fading, this frequency selective fading have a deep fade. We can see that from the figure. This shows the frequency selective fading. Here in frequency selective compared to this S of F and R of F, comparing both, this R of F is different from this S of F. In flat fading, R of F is similar to or identical to S of F. Only a particular all the frequency component undergo equal fading. So frequency selective fading it's a deeper fading compared to this flat fading. So in diversity technique, what we do is, if one of the path undergo a deep fade, another independent path may have a strong signal. So we are choosing or we are selecting the best signal at all the time, and this fading effect then can be reduced. So by selecting the best signal from the strong, or by selecting the strong signal, we are reducing the effect of fading. So a small fading causes a deep and rapid fluctuation as the mobile moves over distance. So this, in the case of small scale fading like frequency selective fading, it causes a deep and rapid fluctuation as the mobile or as the user move over a distance. So to prevent deep fading from occurring, different diversity technique can be employed. So this is called as a microscopic diversity technique. So in small scale fading, the diversity technique is called microscopic diversity technique. And the case of large scale fading, which is caused by shadowing, as we can see that in between transmitter and receiver, if the obstacle is there, which is and if the obstacle has a height which is greater than the height of transmitter and receiver, then the obstacle shadow will act as the receiver. So in that case, a large scale fading occur. So this large scale fading is caused by shadowing of the obstacles on the receiver. So by selecting a base station, that is by selecting a receiver which is not shadowed, the mobile can improve the signal to noise ratio on the forward link. So this is called macroscopic diversity. So macroscopic diversity is by selecting a base station which does not shadow and which improves the signal to noise ratio in the forward link. And the small scale fading or on the microscopic diversity technique prevent small scale fading. Now we will discuss the type of diversity. First one is the space diversity, and this space diversity is also known as antenna diversity. And at the cell site, multiple base station receiving antenna are used to provide this reception diversity or diversity reception. So the space diversity is also known as antenna diversity. And at the cell site, we have multiple base station, and this multiple base station have receiving antenna that are used to provide the diversity reception. And the space diversity reception method can be classified into 4 categories. One is selection diversity, and this next is feedback diversity, and third one is maximal ratio combining diversity, and fourth one is equal gain diversity. So the space diversity is based on antenna diversity, or it's also known as antenna diversity. And at the cell site, we have multiple base station receiving antenna that are used to provide this diversity reception. So this diversity technique is used to decrease the effect of fading, which can be large scale fading or small scale fading. And the diversity technique for small scale fading is called as microscopic diversity technique. And for the large scale fading, which is caused by the shadowing of the shadowing at the receiver or the base shadowing at the receiver is called as macroscopic diversity. So there are two types of diversity technique, that is microscopic diversity technique and macroscopic diversity technique. Microscopic diversity technique is with respect to small scale fading, and that macroscopic is with respect to large scale fading. So based on that, we have different type of diversity technique. First one is phase diversity, and it's also known as antenna diversity. For this, we have a multiple base station at the, or multiple antennas, or we have a multiple base station at the receiving antenna, and this receiving antenna is used to provide diversity reception. Based on that, we have four categories. First one is selection diversity, and this is the figure which shows the generalized block diagram for space diversity. Here we have an antenna up to the, here we have a multiple antenna, that is one antenna 1, 2, 3 etc. up to M, and here we have a G1, G2, that is gain, variable gain, and here we have a switching logic or demodulator, and the output of the demodulator, and at the output of the demodulator we have the receive signal. First one is the selection diversity. Here in selection diversity, there are M demodulator to provide M diversity branches, and each branch gain is adjusted to provide same signal to noise ratio or same average signal to noise ratio, and the receiver having the highest instantaneous signal to noise ratio is connected to the demodulator. In practice, the branch will with the largest signal to noise ratio is used, that is S plus N divided by N. This is the largest N, S plus N divided by N is used. That is the average of signal to noise ratio. So in the selection diversity, we have M demodulator to provide M diversity branch, and each branch gain is adjusted. Here we have M demodulator is there in selection diversity. So we have M branch also, M diversity branch, and each branch have a gain, and this gain is adjusted in such a way that to provide average signal to noise ratio, and the receiver having the highest signal to noise ratio is connected to the demodulator. So from this M diversity branches, the receiver having the highest signal to noise ratio, that is highest average signal to noise ratio, is connected to the demodulator. So in practice, the branch with largest S plus N divided by N, that is average signal to noise ratio, the largest average signal to noise ratio is connected to the demodulator. That is in selection diversity. And next is the feedback or scanning diversity. So it is very similar to the selection diversity, except that instead of always using the best of M signal, the M signals are scanned in a fixed sequence until one is found to be above a predetermined threshold. So here in feedback or scanning diversity, we are not selecting based on this average signal to noise ratio, or instead of selecting the best of this M signal or this M branch, M signal, that all are scanned in a fixed sequence until one is found to be about a predetermined threshold. So based on here we are fixing a threshold and we are scanning the M signals, and one which is found above a predetermined threshold is selected in this feedback or scanning diversity, and this signal is received until it falls below a threshold, and the scanning process is again initiated. And if the signal received it falls below the threshold, the scanning process is again initiated until a signal is found which is above the threshold value. And this method is very simple to be implemented, as only one receiver is required. Here only one receiver is required. So this is a simple method, and this shows the basic form of scanning diversity. Here we have an antenna, and here only one receiver is there. And here we have a comparator. In this comparator, we have a preset threshold. So we are fixing a threshold, and we are scanning this signal from this M signal from this antenna, receiving antenna, and based on this threshold value, a signal which comes above the threshold value is given to the receiver. And scanning is done, or comparing is done until one signal which falls above the threshold value is found out. So next is the maximum ratio combining diversity. So in this method, the signal from all the M branches are weighted according to the individual signal voltage to noise ratio. In maximum ratio combining, we are weighting the M branch signal according to the individual signal to noise power ratio. So according to the signal voltage to noise power ratio, we are giving a weight to the M branch or M signal, we are giving a weight. And then it is summed and added. So this is the M signal. So we are giving a weight to the M signal based on according to the signal to noise ratio or noise power ratio, and we are summing, that is co-phase and sum. Here we are summing, that is a demodulator. So here the individual signal must be co-phase before being get added. Thus the individual receiver and phasing circuit of each antenna element is required in this here. And next, a maximum ratio combining produce an output signal to noise ratio equal to the summed individual of signal to noise ratio, and thus it has an advantage of producing an output with acceptable signal to noise ratio even when none of the individual signals are themselves acceptable. And last one is the equal gain combining. Here in this method, the branch weight are all set to unity, but the signal from each branch are co-phase to provide equal gain combining diversity. So in equal gain combining, here all the branch weight are equally set to unity. Here in maximum ratio combining, we are setting all the branches are given weight depending upon the noise to signal power. That is signal to noise power base. Here we are applying the weight. But in equal gain combining, we are giving weight to all the branch, and we are giving a branch weight that is set to unity. But the signal from each branch are co-phase to provide an equal gain combining diversity. So this is about the diversity or the selection. This is based on the space diversity. So antenna diversity in the base, we have 4 categories: selection diversity, and feedback diversity, maximum ratio combining diversity, and equal gain diversity. So in selection diversity, we have M demodulator. This M demodulator is used to provide M diversity branch, and each diversity branch is adjusted in such a way that to provide same average signal to noise ratio, and the receiver will select one which the largest average signal to noise ratio, that is S plus N by N. And in feedback or scanning diversity, instead of selecting one from the M signal, we are scanning all the M signal, and we are setting a threshold, and the signal which comes above the threshold are selected by the receiver. And in equal maximum ratio combining, we are applying a weight to the signal, and according to the signal to voltage or signal voltage to noise power ratio, we are applying weight to the M branches. And in equal gain combining, instead of looking to the signal to noise ratio, we are applying a unity weight to all the branches. That is, in this method, the branch weight are all set to unity, but the signal from each branch are first co-phase to provide equal gain combining diversity. So here also the signal are co-phase in maximum, as in the case of maximum ratio combining. Equal gain combining, also in equal gain combining, all the signals are co-phased. Here we can see in maximum ratio combining, we have a co-phase and summer. Similarly, in equal gain combiner also, we have a co-phase and summer. So this is about the diversity based on this space diversity